Welcome to our next lecture video for engineering mechanics statics. So in this lecture video, we will discuss about the topic vector addition using rectangular components. So in this topic, we will try to solve problems using vector addition by adding concurrent forces in a force system wherein it may be a two-dimensional system or a three-dimensional system. Addition using rectangular components. So in two-dimensional problems, so we have here an example of vectors A and B. As you can see, it is connected in a head-to-tail manner, forming or following the triangle law of addition, such that if you add vector A and vector B, it will result to vector C. So as you can see graphically, if we break down vectors A and B into components along x and y axis. So as you can see, this is AX, and this one here is AY, which is forming a rectangle. This one right here is BY, and this one right here is BX. So this one is forming a rectangle. As you can see, the resultant force or the vector sum of vector A and B, which is vector C, the components of vector C, which is CY and CX, is also the vector sum of the components of vectors A and B respectively. So for CX, we have the summation of all the x components, which is AX plus BX, and for CY, the vector sum of the y component of C, which is CY, is AY plus BY, using the figure. So that's how we perform vector addition using rectangular components of the vectors. So if we use the vector notation, so as you can see, we have here the vector notation of A and vector notation of B. If we rearrange the equation, we will get this equation, which is AX plus BX for the x component of CX and AY plus BY for the y component of C, vector C. So in general, there are cases wherein the forces added are more than two vectors. So in this problem, we only have two vectors. So in general, if you have three or more vectors, the meaning of summation forces x is you add all the x components of all the vectors that is being added. Example is we have here D plus E. So you should add here dx plus EX. And likewise, for summation forces y, you should add here plus dy plus EY. So basically, summation of all the x and y components of all the vectors that is being added. Same goes by with three-dimensional force system. So for three-dimensional force system, the only difference is that we have the z component, which is the summation of forces of all the z components of all the vectors that is being added. So if we have three vectors right here, let's say we have A plus B plus C. So what will happen is you add here the x, y, z component of the vector in every direction of the resultant force or the vector sum of the vectors, the given vectors. So let's have an example. So first, let's have an example in two-dimensional system. So we have here, using the given figure shown, calculate the magnitude and direction of the resultant of the three concurrent forces acting at point A. So at point A here, we have concurrent force system. So when we say concurrent force system, vector addition is mostly applied in this type of force system, because you can add forces that are concurrent or passing through a common point, meaning all the forces is intersecting at a single common point. In this case, it is point A. So what we will do is, we apply vector addition using rectangular components. So we will break down F1 and F2 into X and Y components. So F3 is not needed to break down because it is already directed to the Y-axis, meaning there is no X component for F3. So what we will do is like this. So for F1, we will break down into, of course, we have X and Y component. For the X component, as you can see, it is a 3, 4, 5 triangle. So for X component, we have 3/5 of 50. And for Y component, we have 4/5 of 50. Next is we have, let's use another color. We have F2. So for F2, we have 10 sine 60 for the Y component and 10 cos 60 for the X component. So as you can see, this is going to the left. So if we use summation forces along X, we should use a negative value for 10 cos 60. Then we have for F3, let's use a different color. Let's say this one. Obviously, it is only a Y component. So that is 60 Newton. So that is, this one right here is negative. So same goes by with 10 cos 60. So that is negative. So it will look like this. If we draw, if we calculate the values, so we have 40 and 30 for F1, X and Y and X component. So we have 5X component for F2. Then we have 8.66 Y component for F2. We have 60, which is for F3. The F3 is only having a Y component. So if we calculate, let's start with X. So we only have two forces along X. We have positive 30 because it is going to the right along the positive X axis, and negative 5 because it is going to the left. So the answer for Rx is 25 newtons. For Ry, we have two forces upward and one forces downward. So that is positive 40 and 8.66, which is going upward, and negative 60, which is going downward. So we will get a value of negative 11.34. So how do we draw the, what will be the orientation of the resultant force, which is the summation of the three forces? So as you can see, if we draw the XY axis, in the given problem, we got a positive value for Rx and a negative value of Ry. So what will happen is, it will look like this. So this is Rx positive and this is Ry negative. So this Rx and Y are the components of the vector sum of F1, F2, and F3. So basically, R will look like this because this is the Rx and Ry are the components. So this is R in vector form. So if we write it in vector form, that is F1 plus F2 plus F3. So we have the values of Rx and Ry in scalar value or the magnitude. So to get the magnitude of R, vector R, you just simply apply the Pythagorean theorem. So you will get 27.5 Newton. And in some cases, we will want, or shall we say in this problem, the problem also asked for the direction. So for the angle of R with respect to the x-axis. So if you want that, we have arctan of Ry over Rx, forming a right triangle. This is theta. Then we have Ry, Rx, and R. So since we have already the value of Ry and Rx, we can solve for theta, which is 24.4. So the answer, So we have also an alternate solution if we want to use the vector notation. So this vector notation is, we will get the same answer, but it is more easier if we use the scalar solution. Vector solution is much easier to use in three-dimensional system. So, but this is only to show you that we will still get the same answer. So the answer will also be in vector form. So continuing to our previous solution, which is this one. Got the two values rx and ry and the resultant. So we will get a final answer of this one. So we have the components ry in negative, rx is positive 25. Then the resultant, the magnitude of the resultant is 27.5. Down to the right, down to the right. Then the angle theta here, which is the direction of r, is 24.4 degrees. Let's have here an example for three-dimensional force system. So we have here 3 ropes are attached to the post at A, as shown in the given figure. So the forces in the ropes are F1 to 60 pounds, F2 75, F3 60 pounds. Calculate letter A, the magnitude of the force R, that is equivalent to the 3 forces. So basically the force R is the vector sum of F1 plus F2 plus F3. The 3 vectors given at, which is concurrent at point A. Then we have the coordinates of the point where the line of action R intersects the YZ plane. So as you can see, this is the YZ plane. Imagine this as a 3-dimensional figure. So we have 3 planes. This is the YZ plane, and this one is the XZ plane. This is the YZ plane. And this one right here is the XY plane. So basically, we want this plane right here. We want to determine at what point will R intersect. What is the value of R? It may be in vector form, but what is being asked is the magnitude. So we just need to calculate its magnitude. And what is the coordinate of this point right here where R intersects? So she is passing in this plane right here. So let's try to solve that. First let's try to calculate first R. So to calculate R, it's easier to use the vector approach. We want F1, F2, and F3 expressed in vector form, vector notation, so that we will have its components, XYZ components, and we can simply add it together to get the vector form also of the resultant force or the vector sum R. So to get the rectangular components of F1, F2, and F3, we just need to apply from our previous lesson. So first, we have here F1. So how did we come up with this solution? As you can see, F1 is passing from point A to point B. So if we draw lines right here, this one is the X, Y, and Z. These 3 arrows, red arrows right here, are the X, Y, and Z component in the direction from point A to B, which is also the same direction as force F1. So we want to calculate the unit vector, which is directed from A to B, because we already have the magnitude of F1. So to calculate that, we have the position vector RAB divided by its magnitude, which is also RAB. So the position vector RAB is simply, you just check out the direction of the arrows and determine its length. So from this one, right here, this distance right here is -3 because you are going backwards, or going to the back from point A to point B. So that is -3. Then we have Y is -12 because you're going to the left opposing the positive y-axis, so that is negative 12. Then we have for z, we have positive 4. So this is positive 4. I will write it again. So we have negative 12 and negative 3. So that is following the triangle law. Connect the components into head to tail manner. So you will get negative 3, negative 12, and positive 4. Then calculating its magnitude R, AB. This is the vector form of the position vector. So you will get the unit vector. And after you calculate the unit vector, you multiply it directly to the magnitude of F1, which is 260 pounds. Then you will get these 3 components of F1. X, Y, and Z components. So basically, this is F1X, F1Y, and F1Z. Next, for F2. For F2, we have only 2 components. We have the X and Z component. So this is negative 3i. And we have positive 4k. So that is here. The same principle applies again and again. You will just remember this, practice this again and again so that you will remember it. Then divide it to the magnitude, which is obviously this is 5 because this is a 3, 4, 5. This is a 3, 4, 5 triangle. So you will get value of multiplying it by the magnitude 75 pounds of F2 given in the problem. So you'll get negative 45i plus 60k. Then lastly, F3 is, we don't need to do anything because it is already in the negative j. So that is one component only. F3 has only one component, which is negative j. So that is negative 60j pounds. So that's how you get F1, F2, and F3. So adding the vectors, obviously we will just simply add the vectors F1, F2, and F3, then combine the common terms. We have negative 60i plus negative 45i, we have negative 105i. Then we have negative 240j minus 60j, we have negative 300j. And we have 80k plus 60k, we have 140k. So this one right here is the vector form of the vector sum, or the resultant of the 3 concurrent forces at point A, or the 3 vectors. So to get the resultant, which is, or the magnitude of the resultant, you just need to apply the same formula for calculating the resultant using the 3 components of a 3-dimensional vector. So we will get R equals 347.3 pounds. So as you can see right here, we have here R has a direction of negative. Obviously, we have the directions and magnitudes of each of the 3 components of the force vector R. So what we will do now is that, so we will answer the second question right here. The coordinates to the point where the line of action R intersects the YZ plane. So to do that, we know that Rx negative 105, Ry negative 300, and Rz positive 140. So it will look like this. We have Rx. If I will draw it here, Rx is negative 105. Ry is, let's say this right here. We have Ry is negative 300 because it is opposing the y-axis. X and Y are opposing to y-axis. But Z is positive. So let's say this is Z. So Rz, or shall I rewrite it again? So this is Rz, positive 140, I believe. So this is the components of R. So if we draw R, it will look like this, R. So this one R, this R right here is this R, this one right here. So it will intersect at a particular point in the YZ plane. The YZ plane. So the question is, what is the coordinates of that particular point? So to do that, we will use the concept of ratio and proportion. So how it will look like? It will look like this. So as you can see, we have the unit vector of R, because we already know that this is Rx, Ry, and Rz. Right there. So this is the point where this is the direction of R, where it will intersect the YZ plane. So if you get the coordinates of that point, obviously it has no it has no x coordinate because it is on the YZ plane. So it will have YD, let's use point D, and ZD. So this is YD and ZD. So the same goes by like here. If you have here a point, and if you call this as YD, and imagine this as a two-dimensional system, the coordinate of this point is obviously YD and ZD in 2 dimensions. But since we have a 3-dimensional system, meaning we have an x-axis, but we don't have an x component or coordinate at that particular point because it is lying on the YZ plane, so you just simply put 0. So to calculate that, we just need to have a, shall we say, ratio and proportion. First is, let's calculate the unit vector, which is lambda. So we have already the vector for R and its magnitude, which is already calculated here. It's 1. So to get the unit vector, just divide it, vector form, and divided by its magnitude. So you will get lambda. Then what we will do is we apply concept of ratio and proportion. So in ratio and proportion, it will look like this. So we have lambda x. Obviously, we will use the positive value because this is ratio and proportion. So meaning there is no negative value. So that the distance are proportion to each other. So we have lambda x. As you can see, this is this one right here. This box right here. So this is, shall we say, this is lambda x. And this one right here. This is proportional only, so it is not meaning this box right here is not the dimension also of lambda x and all the components of the unit vector. So we just use the proportion. So this is lambda z. So as you can see, lambda x is proportion to the 3 feet, 3 feet side of the box. Then we have lambda y, which is this one. This is y, I believe, is proportion to 12 minus yd. Then we have lambda z, which is vertical, proportion to zd. So if we substitute the values of the unit vectors, lambda x, lambda y, and lambda z, let's first calculate this one. Ignoring this part in the equation, you will get a value of yd, which is 3.43 feet. Then ignoring this part right here, then calculating these 2 equations only, then you will get the value of zd, which is 4 feet. So basically, the answer is this one, 0, 3.43, and 4. So that is 0, yd, and zd. Okay, so let's test what you have learned in this lecture video. So we have here some practice problems so that you can try to practice and solve it on your own and check if you have get the answer. And let's start with our first problem. So we have here a 2-dimensional problem. So we have determine the magnitude and direction of the resultant force in the given figure. So take a pause and try solving this problem first. And if you are finished, you can play the video and continue to get or check the correct answer. So the answer for this problem is so for our next practice problem, so we have here a three-dimensional force system. So determine the resultant force in vector notation. So we have here two forces, F1 and F2. So try to solve this problem, take a pause, then come back if you are already finished and check what is the correct answer. So the correct answer for this problem is so thank you for listening to our lecture video today. So I hope you learned something, and I hope that I helped you in your studies and in your engineering journey. And I hope you don't forget to like and subscribe in my YouTube channel for more upcoming videos. And thank you.